All right, time to get started. And yes, I see you, Tioni. The two people I don't see are Megan and Maggie. Yes. All right, on Friday you looked at the structure of the solar system. I know the Flip Friday is supposed to be, you taught yourself that portion, but I just can't help myself. I feel I have to go over the stuff that you learned there. So that's what we're going to be looking at, is the things that we learned from Friday, basically. So the solar system, things that comprise the solar system, of course, first and foremost, there's the thing at the center of the solar system, that star that we like to call, I'm in red right now, let me change to a color we can read it, Sol. It's called the solar system for the simple reason that our sun's name is Sol. Okay. Probably,
Named after the Roman god of the sun, or Roman type of the sun.
Solo.
Or Solo is in Han.
Yes.
Okay, so the sun is the center, the most important thing in the solar system, mostly because it's the most mass, the biggest thing. It's what drives everything in the solar system. So, if you take everything in the solar system that's not the sun, that's 1/700th of the mass of the solar system. That kind of tells you just how important the sun is compared to the other things in the solar system. So what other things do we have? We have the inner planets called the rocky or terrestrial planets. 4 inner planets: Mercury, Venus, Earth, and Mars. Remember, you will have to have these memorized in order and know some trait, whatever trait I ask you about it. You won't be, this is the trait I learned. I'll ask you a trait about the planets. So, inner ones: Mercury, Venus, Earth, and Mars. The outer planets are the gassy planets, also known as the Jovian planets: Jupiter, Saturn, Uranus, and Neptune. Uranus and Neptune are sometimes called ice instead of gas. We'll talk about the differences. But they're fundamentally different. So you have 2 fundamentally different types of planets. Now, let's think back about history. What is the meaning of the word planet? The Greek word planet. Wanderer. Right? These things got the term planet because they were the stuff that you could see moving with respect to the stars in the background. They did have retrograde motion. All of them do, as you probably learned. So that's how they got defined initially. Now, it's pretty obvious to see Mercury, Venus, Mars, Jupiter, and Saturn. Those are pretty obvious. You look out in a dark night, if they're in the sky, you see them as bright things. The others are not so obvious. Uranus was discovered by William Herschel. Actually, he wasn't the first one to discover it. People went back looking at historical records and found somebody had identified that object before. But Herschel was the first person to say, hey, I think this is like the others. And so this thing, Uranus, was the first one that wasn't something that you could just see there bright in the night sky. And in fact, you really can't see Uranus without a telescope. And you can pronounce it Uranus or Uranus. I think I've said that before. I just made my decision.
Can we just call it Uranus?
I don't think so. I don't think that's a correct pronunciation. So this was a new planet. And then from the orbit of the planet, astronomers observed that the wiggles in the planet, we know now that gravity should cause all the planets to wiggle because of the other planets. The wiggles in the planet indicated that there had to be another planet nearby that was affecting the orbit of Uranus. And so astronomers predicted the location and mass and whatnot of another planet that they called Neptune. So Neptune was a predicted planet.
So they didn't know it was blue yet?
They didn't know anything about Neptune yet. It was predicted to exist. They don't name them until they're confirmed anyway. So it wasn't like they predicted a planet, named it Neptune, and then looked for it.
So,
What a weird coincidence. So they then searched where it was predicted it should be, and they found Neptune. Huzzah! They were all happy and cheered. And then as they plotted the orbit of Neptune, they said, now Neptune has some wiggles that don't fit what we know, so there has to be another massive planet out there. They predicted a location and mass, and they searched, and they found Pluto. And so then they all cheered again and said, hoo-hoo, yay, we found it. Until they started studying it. And they realized, no, Pluto doesn't have anywhere close to the mass of what we predicted. And so Pluto was named a planet because it was predicted to be a planet. It turns out as science has advanced, there didn't have to be another planet out there. The things that they were using to predict an additional planet turned out to be differences between the classical Newton's law of universal gravitation, the only one that you really have to know here, and the relativistic gravitation, which is a warping of the space-time continuum. With the relativistic gravity, it explains the orbit of Neptune without an additional object. And so the whole prediction of Pluto was based on a flawed physics understanding. Finding Pluto was just a random coincidence. And so then you have, okay, so Pluto, we called it a planet, it's a planet. Well, we'll learn later in today's lecture about why Pluto got demoted and is now called a dwarf planet, a new category that was made so the dissenters, the people who liked Pluto being a planet, could still say, hey, it's still a planet, it's just the dwarf kind. Okay, besides those things, we have an asteroid belt. An asteroid belt that separates the inner planets from the outer planets. So the asteroid belt comes between the orbits of Mars and Jupiter. And then if we go out beyond Neptune, we have icy objects called trans-Neptunian objects, things that are beyond Neptune. Those icy objects include Pluto. Up until 3 months ago, it was thought that Eris was, well, for about 10 years, it was thought that Eris was larger than Pluto. It turns out that when the New Horizons spacecraft flew by Pluto, they discovered that Pluto actually was bigger than they thought, and Pluto is slightly larger than Eris, even though it's significantly less massive than Eris. But that was part of the reason for Pluto's demotion, was they started finding that Pluto was not alone. It was not unique. There are other objects like it. So we have, yes?
I just have a question about Eris.
Yeah.
Is it pronounced Aries too?
E-R-I-S.
Okay, well I said Eris, and that's the one that I was just wondering.
Aries is A-R-I-E-S.
Yeah, that's another.
Yeah, it's different.
Or,
Eris is a Norse god, I think. Something, actually, it's interesting. The person who has found most of these new dwarf planets, I think his name is David Brown, he wanted to name Eris Xena, as in Xena the Warrior Princess, after the TV show Xena, the Warrior Princess.
Yes.
But that was not allowed because she was not a god, and all of the planets had to be named after gods.
Eris is named after the goddess of chaos.
But everything changed.
And-
Everything changed after
Chaos
Pluto,
is
don't
not
you know?
okay.
Pluto is named after, Roman god at the end of the world.
Yes, but I mean, you change the planets.
This guy knows a lot about his mythology.
Okay, which
Some of
mythology was it from?
mythology nerds.
Greek and Roman.
It was actually Roman. The Greeks had a different name for it.
Yeah, this is all Roman. The Greek stuff is weird.
Anyway, the other dwarf planets have Hawaiian names. Well, Quawar is not a dwarf planet, but Quawar is actually an Aztec name. And then Makemake and Haumea are Hawaiian gods. But,
Make. Make.
yeah, whatever. Okay, so these trans-Neptunian objects are also called Kuiper Belt objects. The Kuiper Belt is a belt that's in the plane of the solar system. All of the planets orbit the sun in virtually the same plane. The Kuiper Belt is in that same plane, just out beyond Neptune. And there are believed to be many, many icy objects out there. And then Oort predicted that there is another cloud that's like 50,000 astronomical units away that is spherically symmetric around us that has more icy bodies. So that's called the Oort cloud. So Oort cloud is a spherical cloud, whereas the Kuiper Belt is in the plane. And we'll learn more about those. All of the comets come from either the Oort cloud or the Kuiper Belt. The ones that have shorter periods, that is, they reoccur more frequently, are from the Kuiper Belt. The ones that have longer times between when they come are from the Oort cloud. Okay, so here's the picture showing the solar system. The first picture over here on the left is, shall we say, zoomed in, so you can see the orbit of the Earth and Venus and Mercury. It ends out here with the asteroid belt. The one on the right is zoomed out, so everything that is inside of the Earth's orbit is inside of this tiny little dot over here, basically. So you can see the outer planets. And then you have the Kuiper Belt out here. Notice Pluto is moving in and out of the Kuiper Belt. At its closest, Pluto is closer than Neptune. At its farthest, it's out here beyond most of the Kuiper Belt objects shown in this picture. Now, Eris has a very eccentric orbit. Eris's orbit is something like, well, no, not that close. Don't be a dork. Eris does come closer at its closest than Pluto at its farthest, but it goes way out beyond where Pluto orbits. So Eris's orbit is something like that. I mean, except for elliptical. You're going to say something, Eliezer?
I didn't know it was that far out. I thought it was a little closer.
Yeah, no, it gets way out there.
Does it come inside of Neptune's orbit?
I don't think it comes inside of Neptune's orbit, but I'd actually have to look it up to be sure. Seth?
So there's potentially something as far out as Eris goes that is technically still orbiting our sun.
Oh, well, definitely, yes. I mean, Eris doesn't come anywhere close to going as far out as the Oort cloud. And we have comets that we know go farther than that.
That are still orbiting our sun.
Yes.
So in other words, if Eris got any closer to the, well, it would take significantly enough closer to the sun, it could very well classify as, or at least look like a comet when it went closer to the sun as it's approaching, right?
Yes, yeah.
It's a ball of ice.
It would be a huge, huge comet that would dominate the sky. But yeah.
That'd be so cool.
So all these planets then are like still like exponentially closer than any of the stars we can see.
Oh, yes. I mean, the nearest star is 4.3 light years away. It's so our solar system, and if you get to the edge of the solar system, they have what they call the heliopause. You have the solar wind, all of the stuff that's blowing away from the sun, and you get to the heliopause, and that disappears. Okay, so these trans-Neptunian objects are out here in the Kuiper Belt, and then beyond that, and notice I put here, I had to modify my slides from last year, not just to make them the way I want to look this year, but also to update because we have new information. Things like I used to say that Eris was larger than Pluto, because like I said, up until 3 months ago, that's what we believed. It turned out the estimate of how much atmosphere Pluto has was incorrect. And so it turned out Pluto was a little bigger than thought, which resulted in Pluto also being a little less dense, which means a little more ice, a little less rock than was thought. Okay, anyway, moving on from this. These delays in opening. And another thing I had to change is last year I had 1920. I swear that came from the textbook. But Pluto was actually discovered in 1930, according to the best resources I could find, Wikipedia. So in 1930, I know to you 1930 seems like a seriously long time ago. It used to seem like a seriously long time ago to me. But, I was born in the 60s. How far back is the 30s? That's not so far back in the past anymore. So Pluto wasn't discovered that much ago, less than 100 years ago. But over the last 20 years, they found a lot more objects like Pluto. And so with the discovery of things like Quaoar, that was the first one that really made a big impact, even though it's not considered a dwarf planet yet at this point, of Eris, of Makemake, and Haumea. Scientists decided that Pluto's odd position as a planet needed to be rectified. So they have these big meetings with International Astronomy Organization where they had people vote on should Pluto be a planet. And the vote was against. And the vote is actually pretty clear cut on why it should not be a planet. Why should it not be a planet? First of all of the planets have big rocks in the cores, right? Pluto doesn't have a big rock.
A little rock.
Well, it probably has a little rock. All of the planets either have a rocky exterior or a cloudy exterior. Well, it has an icy exterior. We have moons like that, but not planets. It's much smaller than all the planets. You know, just step after step, it doesn't fit. So the astronomers, I obviously agreed with the vote, even though I didn't have a vote. The astronomers said, okay, so we can't call it a planet. That just doesn't make sense. Unless we decide that we're going to call any old object out there a planet. Right? So we could say, okay, we have 7,000 planets or whatever. Or we could say, we're going to make planet a special definition that only certain objects can attain. And so what they did is they made a new definition for planet in 2006. They said, we're going to make a planet, it has to fit these two criteria. Number one, it has to have enough mass for gravity to pull it into a roughly spherical shape. Does Pluto have a spherical shape? Sure, yeah. And we knew that back then. We know its shape much better. Back then, Pluto had just a fuzzy surface as far as we knew. Now we have great pictures of the surface of Pluto. But we knew that it had a spherical shape. So Pluto fits that one, no problem. The second one is for it to have cleared out the neighborhood of its orbit compared to its orbit of comparable mass objects. That is, it's got to have no other things in its orbit that are of similar mass to it. Everything else that's around it has to be much, much smaller in its orbital path. And Pluto clearly fails that. Now, there are actually mathematical criteria that they set for these two. So you can just look at the numbers to determine if it meets the criteria or not. But that's basically it. And so Pluto fails this one here. It hasn't cleared out its space. In fact, Pluto's primary moon, Charon, is like, what, 1/4 the mass of Pluto? And so along the way, when they were trying to figure out what to do with Pluto, one of the suggestions was, maybe we should declare Pluto a binary planet. Two planets orbit each other, that Charon and Pluto would be two planets orbiting each other, instead of one being the planet and one being the moon. Now we agree Pluto is the dwarf planet, and Charon is orbiting it as a moon. I find all this stuff really interesting, although it probably doesn't affect life on Earth very much. The Oort cloud, once again, notice that distance. 50,000 astronomical units away. So in this picture, inside of that blue region, that's basically what we were looking at in the more zoomed out picture from 2 slides ago. So now we've zoomed way out again so that we can see all of these icy objects. Now, when I started teaching astronomy, there were no known Oort cloud objects. It was theorized to exist, but not known to exist, except for the observation of comets. My last check, which was a year ago, had about 5 objects that had been confirmed that were believed to be in the Oort cloud. So we're starting to have observations to confirm that the Oort cloud exists, other than having the comets that match the Oort cloud. So, well, we'll talk about comets later. Let's not spend time right now talking about how a Kuiper belt object or Oort cloud object becomes a comet. Instead, let's answer our first clicker question. Which extends the farthest from the sun? If anyone answers, I won't say. I won't say it because somebody will try to do it. Ollie? There we go. All right, we've all answered. We had one person for the Kuiper belt, the only Kuiper belt. 13 for the Oort cloud, and none for the rest. I was going to say if anybody says Earth, but then, there's always the smart aleck. I'll show him that I can answer wrong. So the Oort cloud, of the things we've talked about, extends the farthest. You get beyond there, you get to about 100 astronomical units away from the sun, and you get to the edge of the solar system. How do we know anything about the edge of the solar system? Anybody know? Science.
Is it light?
Eh.
Does it have something to do with the Voyager satellite that finally got out of the solar system?
Voyager. Or, for you Star Trek fans, V'ger. Yeah. The Star Trek, I don't know, which number, 5, something like that, I don't know. Voyager returns to Earth. But part of the name has been rubbed off, and Voyager has developed intelligence, but believes that Voyager is named V'ger because parts of Voyager have been... Anyway, it's
complicated.
It's Voyager just got out of Earth in 1977 and just got out of the solar system.
Yeah, Voyager launched in 1977. Within the last few years, has finally reached the heliopause. We have sent a spacecraft outside of the solar system. And so that's really pretty cool that we have man's influence that has spread beyond the solar system. Now, the Voyager mission was very bold. They were like, we want to make it. Keep in mind, I was in grade school at this time. I actually remember these things. They wanted to make sure that if an intelligent civilization happened upon V'ger somewhere in the future, that they would be able to find us. So they did things like it has a plate that has anatomically correct images of humans, and it has lots of things that are like a history chest. What do you call those things you stick in the corner of the building? Yeah, time capsule of things on Earth, to have recordings on a phonograph, of course, in all of the different languages they could get together, including Navajo. And it's at least theorized, I don't know if it's true, that what the people said in Navajo was, if they try to make a deal with you, just don't do it.
Nailed it.
They have a diagram of the solar system in hopes that if they reach an extraterrestrial intelligence, that extraterrestrial intelligence will be smart enough to decode it and be able to find us and make contact. But then, of course, we've all seen enough science fiction. There is a large segment of people said, we're idiots! We're doomed! Because any aliens that happen upon this are obviously going to want to come and destroy us. And we've just given them the coordinates to come destroy us. The fact is, the nearest star is so far away. Me, my family, my children, grandchildren, we're all going to be cool with this. I do believe Christ will come, or God said, second coming will occur long before any alien life has a chance of finding this.
I don't think any alien life wants to come visit us.
Well, if you believe like I do, you believe there is alien life out there that God created that is watching us, and isn't going to come visit us.
Yeah,
They're like,
Yeah, they already know, exactly.
you're here.
We're the only ones who have fallen, and they are unfallen.
Yeah.
They're unlikely to want to come here.
Yes. Okay, so, I do believe that, but sticking with the science thing, and keep in mind, the science things don't always agree with my religious beliefs, right? When we talk about these things, scientists believe that, there's got to be other life that randomly formed other places, and life here randomly formed, and it's a different worldview. Okay, coming back to this, looking at some comparisons of the planets. Got to zoom in here. Over here we have the sun. This vertical bar on the sun is illustrating its axis of rotation. So the sun is rotating about its axis like that. And then we have all of the different planets here. So here we see the inner planets, also known as the rocky or terrestrial planets. And the axis of rotation is shown for each one of those. And you should notice one of these things is not like the other.
Yeah, why is Venus on the bottom, not the top?
Okay. Why is Venus on the bottom and not on the top? Right? All the rest are on the top. These numbers on top tell you the angle between this line and the axis of rotation for these. So you see, Earth and Mars have very similar tilts. Mercury has no tilt because Mercury is in a locked orbit. And Venus has almost 180-degree tilt, which basically means Venus is orbiting backward. It's only 2.6 degrees off of orbiting backward. And so the question is, why? There are a couple theories on that. One theory, the one that's not accepted, is, hey, the direction we're rotating is random. And it's just random that all but two of the planets are rotating the same direction roughly. And Venus is one of the two that didn't randomly follow the same. That's not the one that scientists tend to believe. The one that scientists tend to believe is that something must have impacted Venus with such a great force and hitting on the side of it that it actually stopped its rotation and made it start spinning the other direction. Now imagine if you're sitting here on Earth and all of a sudden something impacts the Earth that makes us start spinning the other direction.
Well, it would have to get us to stop first, is the scary part.
Yeah. And, we're actually traveling pretty rapidly here. So if that happened, we would all go flying through the wall.
Wait a wall.
Yes, well, the building would too. You're right. It would be absolutely devastating to all life on Earth for something like that to happen.
We survived.
No.
And then
No, because even if you survive the initial impact, you would need to do something like breathe. And you would have dust so heavily mixed with the air, it would be virtually impossible to breathe. And oxygen requires plant life, and the plants would be having a hard time there. And it would be devastating. So that's the theory. Lauren Lee was the one asked.
Is there another theory?
Basically those two.
Just those? Yeah, that's pretty bleak.
Okay, going further out, we have Jupiter, Saturn, Uranus, Neptune. Notice Uranus here, 97.9 degrees. About 8 degrees from being on its side. So Uranus is really odd. As it's orbiting around the sun, during one part, it takes 84 years for it to do an orbit. And during one part of its orbit, its north pole is pointing directly at, 9 degrees away from the sun. And then it comes around and you have the sun on the equator. And then it keeps going and you have the sun on the south pole. Now what would that do to the seasons? Let's imagine Earth was tilted like that. What would the seasons be like?
There'd be a in theory, that whole portion of the planet doesn't receive light, right?
Yeah, there'd be a time of year when virtually half the planet receives no light. What would happen to temperatures there?
It would die.
It would be bitterly cold. And the other side of the planet would have full-time sunlight. It would fry. So you would have really extreme seasons. Remember, the seasons are caused by the Earth's tilt. The 23.5 degree tilt is what sets our seasons. If it was tilted more, the seasons would be more extreme. Tilted less, it'd be less extreme until, if it wasn't tilted at all, like if you look at Jupiter, that 3.1 degrees is virtually no tilt, virtually no seasons. So Uranus would have really crazy seasons. Now notice Pluto also is bizarre. But since Pluto is no longer considered a planet, we don't worry about Pluto and we just say, hey, it's bizarre. It belongs to a different thing out there. They're like ping pong balls. They bounce around. You know, we aren't so concerned about it. So that's looking at the direction of spin. If you look at the plane of orbit, this picture here is showing once again the inner planets, and you see that Mercury is tilted about 7 degrees from most of the other planets for the orbit. So Mercury has the biggest tilt of those inner planets. The outer planets are all very close to the same plane. So we say that the solar system is all orbiting in the same plane around the sun, all the way out until you get to the Kuiper Belt. The Kuiper Belt is kind of in that plane, but as you can see from Pluto, Pluto has a pretty reasonable sized, well actually I probably should go to there, pretty reasonable sized angle for its orbit. It's inclined in its orbit. So there's a 17 degree angle for Pluto's inclination, a 7 degree angle for Mercury's inclination, and I honestly don't remember what the numbers are for the others, but they're all really small. Actually, there's a button to return to no zoom. There, no zoom. So basically we have a plane that almost everything's in. Mercury, even though it's tilted 7 degrees, it doesn't get very far above or below that plane because it has a small orbit. So it's understood that, okay, it's a little more inclined, but it's not really getting much higher or lower than anything else because it's a small orbit. So Pluto's the only one that really doesn't fit with that idea of everything being flat. But Pluto, not a planet, don't care anymore. Makes life easier. Now, I mentioned this in class last period. We can use Kepler's third law along with moons to determine masses of the planets. We have to have a moon to do this. All of the planets, except for, I said one, it's two. Mercury and Venus don't have moons. All the rest of them have moons, so we can just use that to calculate the mass of the planet. We calculate the others by things like looking at the wiggles or sending something to orbit around it. Yeah, so we're able to determine them. We can also, just by measuring the angular diameter and knowing how far away they are, we can determine what the radius of the planets are. And if you know the radius, you know the volume. For a sphere, the volume of a sphere is 4/3 pi times the radius cubed. And so knowing the volume and knowing the mass from Kepler's third law, you combine those two and you can calculate the density, the density of the planets. And what did you learn about the densities of the planets from Friday?
Each planet is composed of different density.
Okay, they all have different densities, but the rocky ones all have densities that are in the ballpark of 5 grams per centimeter cubed, whereas the gas giants are all in the ballpark of 1 gram per centimeter cubed. So there are distinctly different densities telling you about what they're made out of. Pluto is somewhere in the ballpark of 2.
So Jupiter has an ocean?
Jupiter, we'll learn about each planet in care or in detail, but Jupiter, like all of these, it's primarily hydrogen. If you come into Jupiter, the atmosphere gets thicker and thicker and thicker until you get to a point where you're in liquid hydrogen. But at no point would you have a splash going from gas to liquid. Right? It's one of the weird things about gases and liquids. Depending on the conditions, you can have it so there is a noticeable difference when you go from gas to liquid, or you can just continuously move from one to the other. And so going into Jupiter, you would not notice changing from gas to liquid. But if you get deeper, you would then get to a water layer. But that's way down there to get to the water layer. Why? Because water is more dense than the hydrogen. And then, of course, get deep enough and you would hit something solid. Did that answer your question? So no ocean in the normal sense.
How did you figure out the layers?
Okay, how do you figure out the layers? I'm not well, it comes from modeling. It comes from we know what the mass is, we know what the size is, we know what the composition is, we think, and so we say, okay, if we have all this stuff, this much mass, this composition, what's going to happen using what we know about physics on Earth? We calculate what we think is going to be there. So for instance, with Jupiter, they sent the Huygens probe. There was a probe that they let fall into the atmosphere to measure the atmosphere and see if it matched. And they actually found a lot less water vapor than they expected. And so then they were scratching their head, did we just happen to hit a dry spot? Or was our model predicting things just a little different than reality? This being science, it's most likely that they were predicting different. Remember the scientific method, you have a hypothesis to explain something based on scientific ideas that makes predictions, and then you test a prediction. So that's what they were doing with the Huygens probe. They were testing the prediction of the composition of gases. Turned out to be different, so what do they have to do? Well, first, they need to update their hypothesis because they have new information and can make a better hypothesis. And will they send out another probe? Probably at some point, but those things ain't cheap.
And Neptune has a less water, less dense water.
Neptune and Uranus have more water compared to their hydrogen gas. Is that what you're saying? Or
Basically, it's an endless ocean.
yes, although the color is not from water. The color is actually from methane. Right, because you see the exterior is still not water. Come on. All right, so how do scientists come up with a hypothesis about what is going on with our solar system, how it developed? Now, we have here the word model. What's the difference in a hypothesis and a model?
Hypothesis is a educated guess, and the model is the representation.
Okay? So the model is a representation. The model doesn't necessarily have to be correct, but it needs to get you thinking in the right way. And so this model, there are hypotheses, many hypotheses involved with this model. And so it's putting together our ideas about how scientists believe the solar system formed. Now, if we're going to come up with a model for how the solar system formed, we have some rules to help guide us. One is, because the planets all orbit in pretty much the same plane going in a circle, our model has to explain why the planets revolve around the sun all in pretty much the same plane. Number two here, except for the two exceptions I pointed out, Venus and Uranus, the planets all rotate the same direction as they're orbiting. So it needs to have something to explain that. We would sort of like it to. Remember I said there was one that says, hey, there is no reason, it's random chance. Scientists kind of reject that one because it doesn't, we want our model to explain why. And then we need to have something to explain why we have different types of planets, the rocky ones close to the sun and the gassy ones farther away from the sun. So scientists have sat down with these, these are the things we need our model to explain and come up with explanations. The answer that scientists have come up with for how the solar system formed is not that God created it that way. Why didn't the scientists come up with that? Very simply, the worldview of the scientist is a naturalistic view that says everything has to occur naturally. A miraculous event like God doing something is not natural, it's supernatural. And so the scientists rule that out right at the start. They're never going to come up with God did it because they rule that as something that can't occur. So when I talk about the scientific model, I am not telling you God did not create the solar system just like it is. I'm telling you that in a universe where there is no chance of God having done something, this is the best answer scientists have come up with. Now, my own personal belief, I do believe that this is how the solar system formed. You might disagree with me. I'm fine with that. The Bible, I don't think, disagrees with me, or else, of course, I would have some explaining to do to myself. So, the solar nebula theory is the scientific explanation for how the solar system became. So, the solar nebula theory says that we start out as a big cloud of gas, otherwise known as a nebula. So we start out with this big cloud of gas. In that big cloud of gas, you have molecules that are moving around. They have a certain temperature based on their average kinetic energies. And that temperature is just high enough that they're bouncing around and they don't collapse. But then you have a shock wave. Something comes in, like a sonic boom. That's a shock wave. Or a wake, if you go water skiing. The wake of the boat is a shock wave as well. So that comes and it forces the molecules to get a little closer together. Gravity takes over and it starts shrinking. Now, with just the average motions of the particles, you're always going to randomly have just a little bit of rotation. And that little bit of rotation as things come in, you remember Seth up here sitting and spinning? When he pulled his arms in, he spun faster. So when you have this big cloud with just a little bit of rotation, and you shrink it down to this much, much smaller solar system, that small amount of rotation gets magnified to make it a pretty significant rotation. Now, because of the rotation, it's kind of like, was it one of you in this class that was talking about getting into a fight with somebody who's using the potter's wheel? No, that couldn't have been you? Oh yes, it was Keziah. Anyway, of course. So, if you have a lump of moist clay on the potter's wheel, and you spin that potter's wheel, it's naturally going to flatten out. And so that's what they believe has happened with the solar system. The rotation, as it collapsed, naturally causes it to flatten out, and you have lots of collisions. Those collisions tend to make everything equalize into uniform circular motion. So you have everything circling in the same direction because of those collisions. And because of Kepler's laws, which simply result from Newton's laws and the law of universal gravitation, you have the different speeds of things that are closer and farther to give the rotations of everything rotate in the same direction as well. So using our physics as we understand it, this model makes great sense. So the solar nebula theory says that must be how it began. Age, 4.6 billion years ago. How in the dickens would you get an age of 4.6 billion years ago? Yes?
At the beginning, like the origin of the Big Bang is spinning, clockwise, and shouldn't all the planets, all the stars, all the galaxies go clockwise as well?
Well, this isn't the origin of the Big Bang. This is the solar system. The Big Bang would be a different thing, and the Big Bang is coming out of nothing. And so one would expect there to be no spin coming out of nothing.
Doesn't make any sense.
Well, you have some points there. It doesn't make a lot of sense. The origin of the Big Bang, scientists can't even offer an explanation of why it occurred or how it occurred. All they can talk about is, right after the Big Bang, this must have happened. They can't even say what caused it or how it occurred. So there's a lot of questions about that portion of the Big Bang theory. because scientists can't even explain, it's not theoretically possible to explain it. So you don't spend time trying to explain what's not even theoretically possible. Okay, so that 4.6 billion years, instead of passing notes in class, we go outside and grab the note and come back in.
Her mom is out there.
Oh, her mom is out there. That makes more sense. Okay, so how do we get that 4.6 billion years? It comes from a number of things, but the primary one is radiometric dating. Radiometric dating is using the radioactive decay of some of the elements on that periodic table. You look at things on the periodic table, and you have things like uranium. Uranium is not stable. You have a uranium atom, and there is a certain probability every second that atom is going to decay into smaller atoms. Or more likely, what's going to happen is not fission, but it will give off an alpha particle. And we can actually calculate the probability each second that will happen. Now, for uranium, it's not very probable. On average, it will take around 1 billion years for half of the uranium atoms to have undergone the decay. Right? It's a really long time. But we can calculate that carefully, and we can calculate what we call the half-life, the time that it should be for half of the atoms to undergo a decay. And then if we can find a sample of atoms and determine what percentage has undergone decay, we can determine the age. Basically, if you've had it live 1 half-life, you'll have 1/2 of the original atoms remaining. 2 half-lives, you'll have 1/2 times 1/2, which is 1/4 of the original atoms remaining. 3 half-lives, 1/2 times 1/2 times 1/2, which is 1/8 of the original atoms remaining. Of course, there is a really, really big problem in what I just said. How do you know what you started with? We can measure the atoms we have right now, but how do we know what we started with? And so you can take something as simple as carbon-14 dating. You guys have heard of carbon-14 dating, right? Carbon-14 dating can only be used to date things that are 50,000 years old or younger. So 4.6 billion years, that's way outside the range of carbon-14 dating. Carbon-14 dating is irrelevant to anything that has to do with the Big Bang Theory. It's only relevant to things that have happened in the near future as scientists are concerned. Now, if you believe Ussher's chronology is an accurate interpretation of the Bible and tells us that the Earth was created 6,000 years ago, well, then carbon-14 dating becomes highly relevant. So depending on your worldview, carbon-14 dating may or may not be relevant. But going to carbon-14 dating, we can measure the ratio of carbon-14 to carbon-13 or carbon-12 in the atmosphere today. We know how much is there. Once things die, there is no avenue for them to exchange gases with the atmosphere, and so the ratio of carbon-14 to the other ones that they die with is the ratio that they would remain with except for the carbon-14 decaying. And so with something that is relatively young, we can measure how much carbon-14 there is compared to the carbon-12 and carbon-13. And if we knew what the ratio was when it died, we could tell how old it is because we'd know how much carbon-14 has decayed. And so many of you probably heard, we assume that the ratio of carbon-14 to 12 in the atmosphere is constant. That's a first-order approximation that everyone knows is wrong. Carbon-14 dating doesn't rely on that assumption. That's a first assumption, but then scientists have gone and found things that they can verify a date with. Things like, here is a piece of wood that through archaeology, we can date it was created at this time, when the temple was destroyed or something like that. So we have a date on it. And then we measure how much carbon-14 to 12 ratio we have and calculate back, okay, so what was the ratio at that time? And so finding lots of things that have different ages we can go back and calibrate how much carbon-14 to 12 there was in the atmosphere at different times. And in fact, using carbon-14 dating, because the ratio in the air changes over time, you have multiple answers that you get from carbon-14 dating sometimes, and you can assign different probabilities, like there's a 30% chance it's this old, 50% chance it's this old, 20% chance it's this old. Yeah?
I heard that you could use like chunks of ice to figure out carbon is in there at some point.
Well, if you have glacial ice,
Yeah.
glacial ice, if you've ever looked at it, it looks really cool because you have all these little circles that started out as air bubbles that got compressed so they're now flat circles. And so they extract that gas, and that gas is going to have air from back then when it was trapped. And so they can do that. Now that's carbon-14 dating. For dating the age of the universe, or for dating the age of the oldest rocks on Earth, they use things like strontium, rubidium. You look back down there, 1, 2, 3, 4, 5. The left two elements on the fifth row of the periodic table are rubidium and strontium. And so strontium will decay into rubidium, and they can use that. If you go up one row into the other side, you have, actually, no, that's not the right one. It's potassium argon. Just go up one row. Above rubidium, you have K, that's potassium. And then if you go up another row on the other side, that's argon. That's another set of atoms. The potassium will decay into the, actually, I think it's, I don't remember which one decays into which. But you have these radioactive decays that they use for measurements. It gets complicated, but basically using the half-life idea, if they can find a way to determine how much you started with, there's a very complicated method they do that for things like potassium argon dating, then you can determine the age. And I have to stop here because we're out of time. Well, it depends on if you have a beta plus or beta minus decay.
Well, argon is what more stable state, so when it wants to be an argon more than
Actually, the fact is, it is potassium decaying into argon because one of the original assumptions, not the final assumption, but the original assumption is that you start with the melted material and all the argon boils off because it's a gas. But that's not a true assumption, just like saying that the ratio of carbon-14-12 is constant is not a true assumption. And so then they have to go back and find ways to correct it. So yes, it is potassium decays into argon because I remember that aspect.
Do you ever wonder if one day everything that you learn